So we are going to talk about we are going to continue the designing aspect of packed column. What we have so far is so we learn about how to find the number of stage, number of equilibrium stage that we have in the column. And now we are going to talk a little bit about how to find the diameter and the height of packed column, which is another important design parameter. So the most important operating parameter that defines the diameter of the column is the gas flow rate or gas velocity inside the column. And the limit for the gas velocity or the gas flow rate is the floating velocity. So what is explaining in this slide is all about what will happen when we increase the flow rate in the packed column. So when we have a packed column, so imagine this is your column and this is your gas velocity. So when you increase the gas velocity or decrease the column diameter, what will happen? The liquid phase is supposed to go from top to the bottom and gas phase from bottom to the top. So when you increase this gas velocity or gas flow rate, the force of gas phase on the liquid will be much more, the drag force will be much more, and then the liquid cannot flow easily on the packings and go down. So what will happen? The residence time of the liquid on the packings will increase. So this increase in the residence time will also increase the delta P, the pressure drop in the column. And then what will happen? You will have more and more liquid that will accumulate in the packed bed, in the packing section. So the accumulation of this liquid will also increase the pressure drop, and if we continue increasing the velocity or flow rate of the gas, we will reach to a condition that the liquid phase cannot move from top to the bottom, and it will fill the whole column, and we will have a very high pressure drop. That will be our flooding condition. So we will have a flooding in the column, which is a mal-operation. So we have to stop the column, clean it, clean the liquid, drain the liquid, and restart the column, which comes always with some waste of time, waste of money, and for sure some environmental impacts. So we always have to make sure. So like how we can reach to flooding, either by very high velocity or a small diameter. So these are connected. The velocity will define the diameter or vice versa. So what we have to do, we have to know what is our floating velocity, what is the floating velocity, the velocity that we reach to the floating condition, and then we operate a bit below that floating velocity. We always operate, let's say, 50 to 75% of this floating velocity. Okay, so this is our kind of design criteria to find the floating velocity, and after floating velocity we can find the diameter of column. So that's kind of introduction and how we do the calculation. So one of the main method to find the floating velocity is the Shellwood correlation. The Shellwood correlation is also plotted here. Is a correlation that has many parameters that if you plot it, you will have such a plot. In this plot, we have x-axis, which is our liquid flow rate. This is mass flow rate. L, liquid mass flow rate. G is gas mass flow rate, kilogram per second or per hour, whatever. Rho G and Rho L is my gas and liquid density. And here I have pressure drop, which is in meter of water per meter of packing. Per each meter of packing, how many meter of water we have, how many meter of water we have drop in the pressure, or inside this parenthesis you have inch of water per foot of packing. Okay, so those are your pressure drop. So what you have to do, how you use this equation. So let's say you know what's your liquid mass flow rate and gas mass flow rate, you have your densities, you go point, you will calculate this parameter, let's say it gives you this value. Then you know that your pressure drop is 0.25 inch of water per foot of packing, which is 0.25 is this curve here. So you just go up all the way, you remark this point, then you go horizontally and you remark this point, which is here 0.02. So this is your epsilon, which is equal to this term. Okay, epsilon, which is equal to this term. So what is this term? So this term, this equation contains many parameters that I will explain here. So what you will do, you will find epsilon. So once you have epsilon, you have all the other parameters in this equation. Then you can calculate the G prime. G prime is the mass flux, flux of gas phase in the column that at flooding condition. Okay, at flooding condition. So when you have the mass flux and you have mass flow rate, so if you divide this by each other, you will have the diameter of column. So once you have epsilon, you can rearrange this equation and extract G prime, which is a function of epsilon that will be found here. Then you have the density of gas phase, you have all the units here per kilogram per cubic meter. Density of liquid phase, G is the gravitational acceleration. F is a packing factor, will be given to you, is a factor relates to the properties of the packing. This phi is this parameter is a specific gravity of your liquid phase per a specific gravity of water, a specific gravity of liquid per a specific gravity of water, and mu is your viscosity. So as I said, you have this parameter, you have your pressure drop, you go up, you will reach to this curve, and then you go horizontally, then you will read your epsilon. Once you have epsilon, which is this number, you come use this equation and you plug all the information and you will find your G prime from this equation. That is, G prime is the mass flow rate per unit cross-section area of the column. Mass flow rate per unit cross-sectional area, which is kilogram per square meter second. Kilogram square meter second, and for the rest, we have all the parameters. So this G prime is for flooding condition, that you need to use this equation to find your G prime that operating. That we usually, as I said, once we have the G prime, the flooding condition, we use about 50% to 75% of that flow rate as our operating. So we find the flooding from this equation, then 0.25 to 0.70, which is 50 to 75%, will be my operating. So this number times one of this number in this range. This is how we find our G prime operating. Once we have G prime, let's go to Nexus Slide. Once we have our G prime, we have G, which is the mass flow rate, let's say kilogram per second. We have our G prime, which is kilogram per square meter or centimeter, doesn't matter, per second. So kilogram per second divided by kilogram square meter per second, square meter second. So this gives you the area, the cross-sectional area of the column. It gives you this area. Cross-sectional area of the column, which is a circular shape, which is a circle. So once you have the area, you can find the diameter of the column by using this equation. All right. So this is how we find the diameter, and next we need to find the height of packed column. Height of packed column is actually the height of the packing section, okay, where the separation will happen. So if the separation is more difficult, we need taller packed bed. We need a higher amount of packing to do the separation. For example, we have one example here. In general, removing CO2 or removing CO2, let's say we have exhaust gas from an engine, from a power plant or whatever, that it contains CO2 and chlorine. Removing CO2 is more difficult than removing chlorine. So if we use a packed bed, that we use water, so let's say this is my gas that has either SO2 or chlorine, and I want to use water to separate, I want to use water so I want to use water to separate SO2 from, let's say I have exhaust gas that contain either SO2 or chlorine. Separating SO2 is more difficult than separating chlorine. The reason is, if I want to use water, the reason is that chlorine is more soluble in water than SO2. So if I want to use water to separate SO2 or chlorine, in case if I want to separate SO2, I need a higher packed bed. I need a taller packed bed. I need more packing to do the separation. So it really depends on the solubility and how difficult or how easy the separation is. Okay, there are few equations that we can use to find the height of the packed column. Okay, most of them are based on some semi-empirical or theoretical equations. One example is this equation. I'm not gonna go through this equation. I'm just gonna talk a little bit about the terms in this equation. But the most important thing is that to know how to use these equations. So, okay, to find the height can be also shown in Z. We use such an equation. So some kind of theoretical equation that are mainly written based on the mass transfer between liquid and gas phase. So like in this equation, you have all the definitions here. What is like G prime, KOG, like which is the overall mass transfer coefficient. Volumetric mass transfer coefficient, you don't need to know this because it's not very, like critical in terms of, you don't need to memorize it. So here we have the most important things that you need to know. The height is, in this equation, we have two terms. We have this, which is my first term, and we have this part, which is my second term. Okay, the first part, which is G prime over KOG AP. KOG is G prime is the mass flow rate per cross-sectional area. KOG is the overall mass transfer coefficient. A is inferential contact area. It means the contact area that we have for each, let's say, liter of packing. the contact area of the packing per volume of the packing, and P the operating pressure. So this term is called height of a transfer unit. Height of a transfer unit. If you remember, as I said, in packed column, in distillation column, plate column, we have plates. In packed column, we have packing. So sometimes we need to define that, let's say, how many centimeter of packing, how many centimeter or how many meter of the packing can do the job of one plate for me. Okay, so that is the equivalent height, which is also, it can be also written as height of the transfer unit. Is a transfer unit or equilibrium unit that we show it with HTU. The other part here is the number of transfer unit. How many transfer units we have, how many plates we have, or how many this packing section, which is equal to one plate, we have. So that is called number of transfer unit, NTU. So the overall height of the packed bed can be found as height of transfer unit times the number of transfer unit. So we can write this based on liquid phase or based on gas phase. That it depends, you know, it really depends to the mass transfer coefficient that we use. For example, here we have KOG, which is the mass transfer coefficient based on the gas phase. We can have mass transfer coefficient based on liquid phase. So I'm not going to go through this. So it can be either based on gas phase or liquid phase. That I'm not going to go through this because we really don't need to know all these details. For now, just you need to know what is HTU, what is NTU, and that's all. Next, we have okay, number of okay, for the number of transfer units, this term here, this term here, this is my number of transfer units, all this integral. So in some cases, let's say in case we have dilute mixture, it means we have low concentration of our solute, of the component that is going to be transferred. We can solve this integral and have some equations, some correlation that doesn't include integral. So one of the example is given here in this slide. We have it. So number of NTU. So NTU, number of transfer unit, it can be found experimentally or by some theoretical method. So if we have a very low concentration solute, we have a solute that has a very low concentration, we can solve that integral and we can reach to this equation. Yeah? So in this equation you have all the information that you know, like this, for example, y1, y2, x1, x2, those are the mole ratio at the top and at the bottom of the column. X2 is for the bottom of the column. So sometimes we have 0 and n plus 1. Sometimes we can use 1 and 2 simply. 1 is at the top, 2 is at the bottom. Okay, that I prefer to use this type than n plus 1, 0. This is for 1 is for the top, and 2 is for the bottom. Okay. M is the Henry constant divided by pressure, the slope of equilibrium curve, if you remember. Gm is the mass flow rate of gas phase. L is the mass flow rate of liquid phase. So you will have all this information here. You just plug it and you will find the number of transfer unit here is based on gas phase. Next. Okay. For the height, as I said, for the height, we have this equation, okay, that we can still simplify this equation. We can simplify this equation for a very low solute for very low concentration. As I said, this part is height of transfer unit. This is the number of transfer unit. For very low concentration, number of transfer unit for very low concentration in previous slide, you saw that we can convert this to equation similar to this equation, and we can just keep this term like this one, G prime, then we have A, and KOG times P can give us another mass transfer coefficient based on the volume, which is K, we show it with KY in the gas phase. Y is for gas phase, KY is the multiple of KOG times P. That gives us this parameter. So instead of having this equation for very dilute solution or very low concentration of solute, we can have this equation and we can use it directly to find the height of the column. This is the height of packed column. Okay, this is the HTU, height of transfer unit. This is NTU, height of number of transfer units. So we will use this equation, this one here, directly to find the height. No need to go to the other equation. This is the equation that we are going to use now. Okay, now let's look at some examples here together. So the first example is about finding the diameter or the cross-sectional area of the column. So let's see what we have and what is missing. So we are planning to reduce the 2% carbon dioxide in 23 pounds per cent of natural gas stream. So we are going to reduce by 2%. Okay. We are going to reduce by 2% the amount of CO2. We have CO2 in natural gas that has the mass flow rate 23 pounds per second. This is my gas mass flow rate, which is 23 pounds per second. All right. Then using absorption column, in aqueous dimethyl ether flowing out 40 pounds per second. So we have a column. So this is my gas phase and this is my liquid phase. And for gas phase I have 23 pounds per second. For liquid phase I have 40 pounds per second. Okay, 23 for gas, for liquid 40. You want to use 1.5 inch rushing rings. This is the packing that we use, this type of packing to find the packing factor. You want to design for a pressure drop 0.25 inch per foot. So pressure drop is given 0.25 inch of water per foot of packing. Okay, inch of water per foot of packing. And foaming is minimized, so in this condition you won't have any foaming. Under the operating condition, the density of the gas and liquids are: density of gas is given to you 2.8. Density of liquid is given to you 6.3. Okay, density of gas rho G, density of liquid rho L, all per pound foot per cubic meter. The viscosity is also given. This is the viscosity. So what's the cross-sectional area or diameter to be used? What is cross-sectional area? So in this question we are going to use the Shellwood curve. So we have the pressure drop that we want. We have all the densities, the density and the mass flow rate. So we can find the x-axis, we have the pressure drop, and we can find epsilon. Once we have epsilon, we can put in that equation and find G prime. Okay, G prime, this is now like for kind of this is the G prime for the floating condition. We consider for floating condition for now. I mean, this is the minimum in floating condition. We will have the minimum diameter that is needed. Okay, so what we have now, we have to go to the Shellwood curve. So for Shellwood curve, this curve here, first of all, we need to find, for Shellwood curve, we need to find this term, L over G times rho G over L. We have the pressure drop, then we can find this term, okay? We can find this term that from this term we will find G prime. So how we find this term? We have to first find this term that we have to, okay, go here in this equation. So L over G times rho over G power 1, square root. So L, mass flow rate of liquid is 40, mass flow rate of gas is 23, the gas density 2.8, liquid density 6.63. So if you calculate this term, I haven't calculated, but just let me calculate it rapidly here. So it's going to be 40 divided by 23 times square root of 2.8 divided by 6.3. If you do this calculation, you should get 0.37 here. Okay, so then we have pressure drop, which is 0.25. Then we go to the curve. Which curve? This curve here. So this parameter that we call also this parameter the flow parameter, which is 0.367, something like that, which is almost 0.4, right? We consider it 0.4. So we have the pressure drop, which is 0.25. So we will use this curve. So we go all the way up until this curve. We remark this point. Then we go horizontally to see where it cut the y axis. So we will have this is my point, which is between 0.1 and 0.2. So it will be almost 0.15, something like that. So all this term here is equal to 0.15. So now I go back here. I have my parameter here, which is 0.15. Now I need to calculate G prime. I have rho G, the gas density, liquid density, Gc, which is the acceleration, is given. I have also the viscosity. I need to find the packing parameter. Okay, I need to find the packing parameter, and also I need to find this term, which is the specific gravity of the liquid phase divided by a specific gravity of water. Or just let me go check to see what was that term again. Okay, here, yeah. So this mu here is yes, ratio of a specific gravity of scrubbing liquid to that of water. Okay, so either a specific gravity or it can be also the density. All right. So for now, what we can do, we can use the, so here we have, so this parameter, we have we already have density of our liquid, which is 63, and the density of water, which is 62.4. It's not given in this question, but by default in in English system, the density of water is 62.4 pound per cubic foot, right? So this is the ratio of the densities that we have, and also rho g, the densities are given. Gravitational acceleration in English system is 32.2. Viscosity was given 2. G prime is missing, and packing factor. For packing factor, we have 1.5 inch rushing ring, 1.5 rushing ring, or 1/2. So we have a table for that. This is the table that will be given to you. We have rushing ring. This is my rushing ring here, and is ceramic actually. The size is 1.5. So the packing factor will be 93. So I have my packing factor 93. So I plug all the information here, and then I can find my G prime. So you have all the information, you will find G prime, which will be 0.9 pound per square foot second. So now you have G prime, and also you have G, which is 23. This is your G. G over G prime, that gives you A. Okay, so A, the cross-sectional area, is G mass flow rate divided by mass flux, or max flow rate per cross-sectional area. So for G you have 23, for G prime you have 0.9. If you divide them, you will get your A 26 square foot. So, or then you can use this equation. A is pi over 4 d2. So you have A, pi is 3.14. From this equation, you have A here. You can find D, that gives you 5.7. That will be the diameter of your column, 5.7 foot. All right. That was about this question. Please review it, and I'm gonna, if you have any question, we can, as I said, always discuss about it. So last example that we have here. So in previous example we calculated D. In previous example we calculated D. Now we are going to calculate H by using the equation that we have for Z. Okay, so let's see how we use this equation. A packed tower uses organic amine. A packed column uses organic amine. So I'm just gonna plot everything here for you. A packed column uses organic amine. So this is your amine, and then you have your gas phase. Okay. Okay, the entering gas contain 1.26 mole fraction of CO2. So at the bottom of the column, so let me call this area here, I call it 0. I call this 1. This is, I just name it. This is 0, stage 0, this is stage 1. So I have my Y0 here, which is the CO2, 1.26% or 1.126. All right. Then and the gas that contains CO2 is a gas, natural gas, let's say, or exhaust gas with CO2. It will arrive with this amount of CO2. This is the mole fraction of CO2, and it will leave at the top with this much CO2. At the top, it will leave with 0.04%, or the mole fraction is going to be 0.004. Okay. The amine enters pure, so the amine that is arriving, let's say X1 at the top, is pure, is 0. And if the amine left in equilibrium with the entering gas, so amine here, it will leave. So amine will leave here, but once it leaves, it will be in equilibrium with this gas. So in equilibrium means there is an equilibrium relation between Y0 and X0. Okay, Y0 and X0. So then it would contain, okay, the amine leave in equilibrium with the entering amine gas, it would contain this much CO2 when it is leaving. Okay, when it is leaving, which is in equilibrium with this Y here, it has 0.8% of CO2, or 0. If I want to write it, 0.008. Okay, this is the amount of CO2 leaving the column. So this X is also in equilibrium with Y. So the gas flow rate, this is my gas flow rate here, G, and here I have L, my liquid flow rate. The gas flow rate is 2.3 gram mole per second. The liquid flow rate, L, is 4.8 gram mole per second. All right. So the tower diameter, the diameter is given 40 centimeter. This is your diameter. The overall mass transfer is also given. Overall mass transfer is also given, 5 times 10 power. How tall should this tower be? You need to find Z in this column. So how we find it? We will have to use the Z equation that we have. But before we doing so, we need to find Okay, so first of all, okay, this is not X0 that we want. Okay, this is okay. This is okay. It's saying that if the amine that leaves the column and it becomes in equilibrium with the gas, the amount of CO2 will be this much. If the amine that is leaving the column reach to the equilibrium, it will have this much CO2. If it reaches to equilibrium, it will have this CO2. But this is my CO2. But in general, in reality, it doesn't reach to equilibrium. So if it reaches to equilibrium, I just put a star for equilibrium. But in reality, it has a certain amount of CO2, because in reality they are not in equilibrium. It doesn't reach to equilibrium because my column is not perfect column. It never reached to equilibrium. So in reality we have this much x0. In equilibrium we will have this much. So to use the z equation, I need to have all these parameters, x1, y1, y0 and x0. How can I find x0? I have x0 star in equilibrium. If it reaches to equilibrium, it has this much. But in reality, that is now, I have to calculate this parameter. How can I find it? I can write the a balance on the whole column. Okay, how can I write the balance? So I can say that whatever CO2 that is going from gas phase, it will be received by the liquid phase. So how much difference we will have in CO2 from bottom to the top, how much change will be in the CO2 from bottom to the top will be going to the liquid from top to the bottom. So by considering this, I can write the balance for CO2. That the balance will be this equation here. Okay, so that's my balance. So I have y0 here and y1. This is my gas phase, and this is my liquid that I have x1 and x0. This is my liquid phase. So whatever change I have in the gas, which is here I have more CO2, here I have less. So the difference times the gas flow rate, that gives you the amount of CO2. So this is the column cross-sectional area, which is not an important parameter. You can just eliminate it. So the difference in the CO2 in the gas, which is the difference in the mole fraction times the gas flow rate, is equal to difference of the change in the mole fraction of CO2 in the liquid phase times the liquid flow rate. Okay, so we have all these parameters. We have G, which is 2.3, Y0 at the beginning, at the entrance is 1.26 percent, at the bottom is 0.04%. So this is the change in the gas phase. For the liquid phase, at the top I know is pure. At the top is pure, is 0. I have the mass flow rate of the gas, but I don't know what will be the amount at the end. As I said, if it reached equilibrium, I don't know what is the value, but in reality, in the real operation, I will have to find it by using such a balance that only parameter in this balance which is missing, which is x0, so that will be 0.00585. So this is about x0. Next parameter that I need to find is m, because I need this m in the z equation that you will see in the next slide. So as I said, if this x reach to equilibrium with this y, I don't know what is its value. It's already given in the previous slide I have given to you. So if it reach to equilibrium, the value will be this much, which is a little bit which is a little bit bigger than that one we have here. That makes sense, kind of. So if it reaches to equilibrium with this, it will have this much x, which makes sense. Why makes sense? This value in which we have equilibrium is bigger than this value. Equilibrium means more efficiency. When we have really a perfect column, it can reach to equilibrium, so it will absorb more CO2. That's why it has more CO2. That's why this mole fraction is bigger than this one here. So I have this relation between y0 and this x in equilibrium, which I use the equilibrium line. Then I have y0 already given to me, x in equilibrium given to me. The only missing parameter here is m. the Henry constant or equilibrium constant. I need this M to put in this equation to find Z. So now I have almost everything that I need. Now I will go to Z equation, the next slide. That's my Z equation here. So this, okay, one important note, this equation was kind of written in the wrong way in your notes that you have. So I have updated this presentation, is updated one available on the D12. So if you are using the hard copy, just correct G in your slide to G prime. This should be G prime, okay? So G prime, which is G divided by A, okay? So now we need to use this equation. K is given, okay? K is, actually Ka is given to you. Ka, all these two parameters is given to you as 5 times 5 times 10 power minus 5. These two together given to you as the mass flow, volumetric mass flow, mass transfer coefficient. And we just found it. G we know it. L we know it. Y0, X0, Y1, X1, they are all known. So we just need to put this equation here. So G prime is G that we know divided by A, area, cross-sectional area. The diameter of column is given D. So we can find area, which is P over 4 D power 2. So P over 4 D power 2, that will be your area. That is your G here. This is your area. G over area give you G prime. This is your mass transfer coefficient times A all together. M we just found it. G we have it. L we have it. We have all this information that we need here. We just plug them. If you do so, you will find the height of the column 3.2 meter. This is how you will calculate the height of column here.